Good morning. Oh, good afternoon. Okay. Yeah. Yeah. So, good afternoon, everyone. My name is Ning Zhang from Nanjing University, and very thankful for this amazing conference because I usually attend ICUC all the time, and it's a very good opportunity to share what we have done on the urban data and mitigation. But in this talk, I'd like to expand this story to more than urban data, and I think we had have a lot of wonderful talks in this session, including this morning. And I'd like to move to a little to air quality thing. And then, okay, a very short background introduction. And as we all know, in the recent decades, China has a very quick urbanization process, and also we have a very strong urban pattern observed even in each cities in China. And also some statistics work based on the observation analysis that show urbanized induced change increase the heat wave days number in China based on the dataset from 1960 to 1914. And also on the air quality thing, with the urbanization and the industry of China's development, we suffered sometimes a very bad air quality problem. But began at 2013, due to the strong control policy of China government, and we have very dramatically improvement in the air quality in most cities in China. We can show the decrease in both particle SO2 or NOx or CO things, but that's a different story on ozone because in most cities we observe an increase in ozone concentration. And when we came to some big urban cluster or urban groups, such like Yangtze River Delta, and we can see very strong correlation between urban heat-line intensity and surface ozone concentration in the air quality data. And some Chinese scientists or some researchers that name this synergistic effect because we may both serve from high ozone concentration and strong urban heat-lines. And based on this, because we also can do some mitigation for urban heat-lines. For example, green roof and coral roof and so on. This may reduce the urban temperature. And there's another thing we can see. If we reduce the surface temperature, maybe we reduce the chemical reaction related to ozone. So we will be benefited from this. Okay, so basically back on the previous study on our group on coral roof and green roof in this area, we found that coral roof and green roof can reduce urban surface air temperature, but the urban boundary layer maybe become stable and lower due to also due to the reduce of surface temperature and increase the boundary layer stability. So on the particle or tracer gas, this process may increase the surface concentration, but on ozone, different results from different researchers or in previous studies, we can say maybe coral report on coral roof decrease surface ozone, and maybe quite a different story are told. And also, as mentioned in Oak's textbook, Urban Climates, usually we have different urban circulation type and different weather background. Some kind we can call it urban doom because it occurs usually under a calm and stable weather condition. And when there's some ambient regional wind background, we got urban climate. Okay, our another questions will there be different effects under these conditions or not? So basically, back to Yangtze River Delta because usually in each summer we have long heat wave events, varies from weeks to nearly months. So mostly due to the analysis on subtropical high pressure system. And under such heat wave events, we also observe a high surface ozone concentration especially in cities. So in this study, we just take Shanghai as a megacity example. And our research method is based on usually numerical modeling because it's much cheaper than observation and easier. And also we design our case. We use the urban canopy model and change the roof albedo and the gray roof coverage because also it's an easy way. Because we now we have very useful method in the Wolf model to consider this, and we pick three three cases for our studies, and two dome cases and two urban plum cases, and we can show, and we also set 6 sets of experiments. In the control, we just use the Wolf default roof albedo and without gray roof, and the G means the gray roof case, and the O3 means we just add 30% gray roof cell, and also the same thing to the other cases. And first, we can see, as our previous studies found, both cold roof and gray roof have very close cooling effectiveness, especially in these cases, and also we can find more stable urban boundary occurs. Okay, we have this slide shows the decrease in urban boundary heat, and we also can see in the cold roof, the urban heat mitigation just comes from the decrease in surface net radiation, and for the gray roof, they actually change the urban surface Bowen ratio. But if we go deeper into the air quality thing, we just found when we deployed cold roof or gray roof, we also weaken the urban hinterland circulation because we just reduce the temperature difference between the urban and the non-urban area, and then the surface ozone concentration increase in all cases, both in the urban dome and the urban plum case. And in this slide, we also can see such increase in the near surface ozone concentration this effect can be transported downward in the plum case. And also we can observe the decrease of ozone concentration. And if we take a look at the thermal variation, also observe the same thing increase in the in the bottom of the boundary layer, and also a decrease in the upper part. Okay, if we take a look on the ozone precursors, for example, NOx and VOC, we also can see after we employed cool roof or gray roof, we make the boundary stable and we trap more ozone precursors in the boundary layer. And because the weather condition is also hot enough, so the chemical reaction also can carry on, and this increase the ozone concentration. And then we try to quantify these different processes using what we call the IPR method. This is the default mechanism you just can switch on in Wolfram, and then they can divide the change in ozone to the impact on advection and on mixing and also chemical processes. And then we can find, then we just divide the urban area in our simulation domain into two parts. And the part one is what we call the loner boundary layer, but this is not exactly the bottom part of boundary layer because the boundary layer have a turnover variation and we didn't consider in this analysis. And from 750 meter to 2 kilometer, we need it part two. And I'd like to show here, we can also enhance chemical processes contribution for the ozone concentration in both part A and part 2. And the horizontal advection and vertical advection contribution is maybe different. This always related to the weight of the urban hinterland circulation. Also, if we just take a look at the turnover variation, also we can find when this changes most occurs at daytime. Okay. Okay, so we also try to do some calculation on how the urban area can suffer from high temperature or high ozone concentration. You can see we do increase the suffering area or time with current roof and green roof, but we also increase the ozone hazard like that. Okay, a very short summary. First, green roof and core roof can effectively mitigate the urban hinterland. That's what we have talked a lot. But in some cities, such like maybe a lot of Eastern China cities, they have air quality problem. The surface ozone may be also increased. So, for example, before we try to mitigate urban hinterland, maybe we should consider some trade-off between meteorological and air quality thing. Okay, thank you very much, and I will take questions.
Thank you. We might have time for one question. Any question?
Thank you for your presentation. I wonder how do you choose the tree density or tree height in the remote simulation phase?
Okay, so we just use the default green roof scheme, developed by Dr. Yang, Jiazhuan Yang. I think he's also in this conference, and maybe the detail you can go to his paper on 2015. So it's just I think they just put a very short vegetation and consider the irrigation on the roof of vegetation thing. Okay.
Thank you. All right. Our next speaker is Dr. Ning talking about effects of trees.